The next topic we want to explore is comparing sets. How do we compare sets? How do we know if two sets are equal? And how do we define a subset of another set? So the first thing that we might be interested in is whether or not two sets are equal. Because in sets, order doesn't matter. The representation of two sets might be very different. The order that things are listed in might be different. And so we need a means of checking formally if two sets are equal. Well, we say that two sets are equal, and we denote it just using equality, if A and B have exactly the same elements. Okay, so if an element X is in A, it's in B, and if it's in B, it's in A. So it goes both directions. If X is in A, X is in B. If X is in B, X is in A. They're not equal, and we denote that with the not equal sign that you're familiar with. There's an element in one of the sets that is not in the other. Okay? So if there's an element in A that's not in B, or there's an element in B that's not in A, then these are not equal sets. Well, let's take a look at a few simple examples. Here we have a set A, which is equal to 1, 2, 3, and B is equal to 2, 3, 1. Are they equal? We would check that 1 is in set B, check. 2 is in set B, check. 3 is also in set B. So if it's in A, it's in B. But does it go the other way around? And we can do this same exercise. 2 is in A, 3 is in A, and 1 is also in A. And so these are equal sets. And this is a small set, obviously, so it might have been very obvious to you. But this is the same approach we take for even larger sets. So we loop through all of the elements in the set and make sure they exist. And we can do this again with the following two sets. So we have the set 1, 2, 3 is set A, and we have a new set C, 1, 2, 3, and 4. And when we do the check from A to C, we can check that 1 is in A, 1 is in C, 2 is in C, 3 is in C. Works out fine. But when we go the other way around, we quickly see that we're fine for a while. 1, 2, 3 are all in A, but 4 is not. And so these sets are not equal. A is not equal to C. So we're going to take that same set C and compare it to another set, and our set D here. It's a bit bigger. So when we check, we can check that from C, 1 is in D, 2 is in D, 3 is in D, and 4 is in D. When we go the other way around, it might seem obvious that we're going to have problems, but in fact we don't. We just have to do some extra checking. 1 is in C, 2 is in C, 3 is in C, 3 is in C, 3 is in C, 3 is in C, and 4 is in C. And this part might seem a bit funny, but in fact these sets are equal because order and repetition do not matter. They just do not matter in sets. And so we saw in our first example up here that order didn't matter, and in the bottom one, repetition does not matter either. So sometimes we want to take a look at sets and figure out if they belong to another larger set. And we consider something to be a subset of another set. So A being a subset of B, which is denoted as such, if every element in A is also an element of B. So in our Venn diagram, what it means is that we could fit the representation of that set inside of the other set. Okay? So it means that if X is in A, it implies that X is in B. So it's almost half of the check that we did for equality, right? We checked that X was in A, meant that it was also in B, and then we went the other way around. We checked if an X was in B, an element was in B, it was also in A. Furthermore, we can define a proper subset using this notation if A is a subset of B, but they're not equal. So it's possible to be A to be a subset of B and them to be equal. And you can see that even in that notation, that looks a little bit like the proper subset with the half of the equal sign built in, because it might be equal, but it's certainly contained within. Okay, so this could push out to the boundaries, but it won't go past those boundaries if it visually. But if it's a proper subset, then there's some element out here that that is not in A, at least one, so that they're not, such that they're not equal. So let's look at a few of these sets as examples. So we can see we've got the set A, which is 1, 2, 3, 4, 5, 6, 7, 8, 9. We've got the set B, which is the evens within that, 2, 4, 6, and 8. We've got our set C, which is 2, 3, 5, and 7. A set D, which is everything that's in A, such that x mod 2 equals 0. And we could do a quick check that those elements for which x mod 2 is equal to 0 means if I divide x by 2, I get a remainder of 0. Well, those are just the even numbers, aren't they? And so that's 2, 4, 6, and 8. And we're going to need that in a second. And E is defined as all x in z, so all integers, positive, negative, 0, such that x is prime and x is less than 10. Well, the prime numbers we know are 2, 3, 5, 7, 11, 13, carry on, but I can stop because I know it's all those prime numbers less than 10. And so in fact, that is just the set containing 2, stop me when I get to 10, 3, 5, 7, and that's the last one because the next one is 11. Okay, so now that we kind of know the elements in our sets, we can think about whether or not the following are true. So first question, is A a subset of B? Well, no, because there are elements in A that are not in B. And so we know that this is not true. And if it's not a subset of B, then it's certainly not a proper subset of B. So now we can go the other way around. Is B a subset of A? Well, we can check that 2 is in A, 4 is in A, 6 is in A, and 8 is in A. And so B is absolutely a subset of A. Is it a proper subset? So what that means is it's a subset of A, but it's not equal. And we can check that it's not equal because there are elements in A that are not in B, all the odds. And so it's in fact a proper subset. So let's move to the next option, and that is an exploration of A versus C. So first we're going to check if A is a subset of C. And it's pretty quick to see that there are elements in A that are not in C. So many of them, in fact. So all of these. The only ones that exist are C themselves, but there's 1, 4, 6, 8, 9 are elements in A that are not in C. And so they're outside of that. I can't fit the Venn diagram of A inside the Venn diagram of C. And so this is not true. It is not, A is not a subset of C. And in fact, if it's not a subset, it's not a proper subset. So I don't even have to consider that property. So what about C as a subset of A? We can check, so we're checking that 2, 3, 5, and 7 are elements within A, and we can see that they are. So, in fact, C is a subset of A. And more importantly, if we want to check if it's a proper subset, we see that there's still elements in A that are not accounted for. And so C is a subset of A, but they're not equal. And so that means that, yes, C is a proper subset of A. If we compare A and D, we're going to see the same issues. So D is those elements 2, 4, 6, and 8. Well, that's the same as B. B and D are the same, and so the relationship between A and B will be the same as the relationship between A and D. D and B are equal, and you can check that if you wish, but they are absolutely equal. They're the same sets, each containing the elements 2, 4, 6, and 8. And so we can immediately say they have the same relationship with A. D and B have the same relationship with A because they're equal sets. So the only thing left to check then is A versus the set E. And E, we remind ourselves, contains 2, 3, 5, and 7, all those prime numbers less than 10. And that means that A and E have the same relationship as A and C. And so we get the same result. So we have one last set of relationships to explore, and that is B versus D. And D, we've said, contains 2, 4, 6, and 8. And so we can check that all the elements of B are also in D, and so we know that B is a subset of D. It's not a proper subset because there's no element in D that isn't in B, and so B is not a proper subset of D. And that's because we're going to see that these two sets are equal. And the way that we know that's true is we can then check D is a subset of B. Every element in D, 2 is in B, 4 is in B, 6 is in B, and 8 is in B. So D is a subset of B. But D is not a proper subset of B because, in fact, for that to be true, D and B must not be equal. There must be something in B that's not in D. In fact, because we have B is a subset of D and D is a subset of B, that's the same as saying B and D are equal. Because what we've done to find those 2 points is to check that every element of B is in D and check that every element of D is in B. And that's what we needed to do to check that B and D were equal.